Okay, dear fellows, today is our second lecture on the series of design of compression members. Compression members, as we know, is or columns that essentially take the loads in compression. Okay, we knew from the last lecture, we can recall that a column can fail due to, there are two major mode of failures for column. Number one, it's material failure. So material failure can occur because while fabricating the steel sections in industry, residual stresses develop in steel. So a steel may not reach its Fy, actual Fy, which is 36 KSI for A36 steel. So it may fail earlier. So a material failure may occur. And according to, so in this case, we use a squash equation to design or analyze a column. Okay, there is another type of failure which is called a geometric failure. It is governed by which equations? Euler's equations. So it's actually a type of a buckling failure. It states that column may, when a load, a compressive loads increases, a stage reaches when P becomes P critical and stress become F critical and a column may buckle. So they are essentially two modes of failure of a column. So from previous lecture, I can recall that I had to find the slenderness ratio of a column. So slenderness ratio of a column is L by R, its length, and its radius of gyration. So radius of gyration is actually I by A. So I is the second moment of area, second moment of inertia, and area is area of cross section. For example, for a rectangular section, if I have a rectangular section and if it's P and it's D, then I would be PD cubed by 12, and area is obviously PD. So in order to know whether material failure or geometric failure would occur in a column, I have to find the slenderness ratio. So I have to multiply the slenderness ratio with K as well. Now this is the support condition. Like if both the sides are hinged, then we use K value equals to 1. And there's a table for every type of support. Okay, first of all, you have to find the slenderness ratio, and you have to find this value as well. This parameter is lambda r. So this is actually a boundary condition. It's equal to 4.71 E by Fy. So E of steel is 29,000 KSI, and Fy is, for example, 60 KSI, 36 KSI for E36 steel. Okay, and then you have to find this lambda r value, and you have the KL by R value. So you have to find if your KLR value is less than this lambda R value or greater than. If it is less than this value, so again I am telling you, if your KL by R, that is slenderness ratio or modified slenderness ratio according to support, so K is the support factor, if it's less than lambda R, which is 4.71 E by Fy, and it depends upon your steel, then inelastic buckling would occur, and the failure would be governed by squash equation, and this equation would be used. As it's a material failure, so you can see Fy's all material parameters have been included in this equation. Fy is material, you are modifying this Fy, and if your KL by R is greater than 4.71 E by Fy, then elastic buckling would occur, and Euler equation would be used, and your F critical would be 0.877 multiplied by F effective, and F effective is very easy to calculate. This is F effective, and it has been derived from the same equation, Euler's equation, from the previous lecture. You can see where F effective comes from. So it's very easy. You have to listen to the previous lecture as well. So it was very simple. You should listen to previous lecture, and before uh, studying this lecture. So this question was solved. I told you to solve this. It's very easy. uh, from the top view you can see that this is x and this is y axis, so you have got two different support conditions. For x axis, two supports are hinged, so k value would be 1, and one is hinged and one is fixed for y axis, so it is 0.7. Now there is a table for this k value, and it's you can find it from the manual. You can find it in the manual as well as in the book. So this question is very easy and you should be solving it. I'm going to solve this question. Now this question is a design problem, and it states that you have to design a column, and there are some conditions which are given. You are given the length of column, that is 26 feet, but he has multiplied this L with K. So no information about supports are provided. However, the KL value is given, so it's easy to calculate the slenderness ratio. So I don't require the support conditions. Okay, the A992 steel is used, so you should know that Fy should be 50 ksi. If it was A36, then it would have been 36 ksi. Dead load is given. Obviously, the column is subjected to dead and live load, so it's given. And there is one condition that you have to select the W18 shape. You have to select a shape, a W shape. Now, it could be a channel, it could be an angle, but it is a W shape. And it's W18, it means 18 inches. And you have the liberty, you have the option to select the W18 shape. It may be W71, W60, anyone. It can be anything based on it should be based on your design. So first of all, I have to design this. So again we are using the integrated approach. So I have the option to use AST and LLFT. So I'll be solving on both. So you should be in the exam it is mentioned that you have to solve it either on LLFD or ASD or integrated approach. So in our course we have to follow the integrated approach. Okay, first of all, I have used this equation, a very simple equation. That equation is PU ultimate load is phi Fy Ag. So this equation has been used in the last lecture in the first numerical of example 1. This is phi factor for LRFT. So here I don't know, Fy is obviously 50 ksi, but in a column a material failure may occur. Now you know that if a material failure is occurring, then Fy is equal to 50 ksi may not be reached. It may fail before 50 ksi. What is material failure? Material failure states that a column never reaches its Fy value. For example, for A992 steel, it is Fy is 50 ksi. So it may fail here under loading. So this is a material failure. Okay, what is a geometric failure? The geometric failure says that a material reaches 50 ksi but it may buckle. So here I don't know what mode of failure would be followed, whether it would be a material failure or geometric failure. So I should not presume that my steel is 50 ksi. It may fail, it may suffer a material failure. So that's why I have to change this Fy into F critical. So my all energies would be consumed in calculating this FCR. So this is very important point. You don't know what your Fy is, although it's A992, but in a material failure Fy is not reached in compression member. This is the main point of material failure. So I am using this equation, which is Pu is equal to phi FCR and Ag. And your ultimate because this is LRFT, so you have to use a factored load 1.2 and 1.6. If it was AST, then you would have simply added dead load and live load. Okay, PU comes out to be 600 kip, and I have put this, and this is 0.9. This should be given. So you have been able to find AG, but I don't know the FCR. I just know the FY, which is equal to 50 KSI, and I am not sure that a material failure would reach or not. I mean, it would be a material failure or geometric failure. So that's why I have to use the F critical. So I'll assume F critical equals to 2 by 3 of Fy, or it may be 66% of Fy. This is a safe bet always. So you should do always that. I mean, you can assume FCR equal to 50% of Fy, but it would be too conservative and too uneconomical design. So it's always better to go for 2/3 of Fy or 66% of Fy. So I've done that. So my FCR comes out to be 33.33 KSI, and this is given. So I've put this in this equation, and my area comes out to be this. Now I have chosen this W18 into 71 because my area is 20.9. So how I have chosen that? It's very simple. 18 into 71, W in 18 into 71, this one, the area comes out to be 20.8. You can see that 20.8. So I have chosen that. Okay. Okay, and this property R minimum is also from the table. I mean, this is also from the table. It can be found out from the same table, radius of gyration. So you have to take the minimum of this. I mean, there are two Ry and Rx would be given, but you have to take the minimum of two R values. I mean, I can go back. It's very easy, but I have to tell you again. And 18 into 71, okay, and I have two values, 6 and 10 R values. So I have two values for 7.50 and other is 1.70. In order to maximize the slenderness ratio, I have to use the minimum, and it is 1.70. Done. Okay. Okay. Next, my slenderness ratio. I mean, it's very easy. The KL is given. R minimum I've just found out. It comes out to be this. And next, the famous table, famous graph, which is somewhat like this, and lambda R is 4.71 E by Y, and 4.7, my F lambda R value is 113. My slenderness ratio is 184. So I am here. So I'll be using Euler equation. It means my failure is a geometric failure. I am here. You must remember that I am here. So I am here. I am somewhere here. So I'll be using this equation, and it's elastic buckling. It's a geometric failure. So a geometric failure occurs. So I have to use this value. F effective is very easy. You have to use this formula. You have all the values. So it comes out to be, F critical comes out to be 7.46 KSI. Originally you assumed it to be 33.33 KSI. Again, I put this back in this formula, which is original formula, and it comes out to be 140 kip. Your column would resist 140 kip load. However, the demand is 600 kip. It means not okay. So I have to reconsider my priorities and I have to redesign it. So I've used another W18 into 13 shape. I'll go back to manual because its demand, well, capacity is 140 kips, which is far lesser than 600 kip. So I have to increase the area. So that's why I've chosen the W section having larger area or greater area. Again, I went back to that manual and I found out the minimum of two values, Rx and Ry. The minimum of two would be governing. I'll calculate the slenderness ratio. Again, I have calculated this. This comes out to be 113. My slenderness ratio is again greater than lambda It has been found out because this is 116 and it is quite near to 113. So my major concern is geometric failure because the region I'm here, it is 113 and my slenderness ratio is value is 116. So I've used again the same values and I've resolved it, and my answer is 720k and it is greater than 600k. So I mean it would be governing 720k, but as you have to use the LRFD, you have to multiply it with 5, and the 5 factor is 0.9 that would be given in the paper. It's very easy. And again for ASD, this would be 1.67. I mean that can be, it's very easy. The thing is, you should know that 648 is quite near to 600k, and it's as it is quite near to 600k, it's an economical design. Most of you people, who have solved the mini project, they have computed the block share about to be double of that of demand. For example, this, or sometimes some of you have found the answer as this and written as okay, but this is not okay. It's highly uneconomical. So you have to choose the area with lower area, and that would be economical. Choose the section with lower area. Okay, for ASD it's very easy. Again, I have used the same consideration. Here the formula, there would be no phi. The loading is just simply the summation of dead and live load. Again, this would not govern because this is the 18 into 71. Okay, my demand here is 400 kip, right? Because the load for ASD is 400 kip. Again, this is 2/3 of it has been, it's same, it's very easy and very same. Here this would be used, which is 1.67. In the last question it was used, it was 0.9. So you should know that 0.9 into 1.67 should be equal to 1.5. It means phi when multiplies with factor of safety should give 1.5. Okay, W18 into 13, this was my chosen area. Gross area is 30.8.3 and R minimum is 2.70 inches, minimum of 2. W18 13, W18 13, W18 into 13. So it should be below that. Okay, W18 into 13. I am unable to find the W18 into 31 or 13. 18 into 35. Okay, it must be 31. I don't know. 8 minute. W18 into 13. So I think it's W18 into 31. It should be wrong. Okay. It is W18 into 31, I think. W18 into 7650 and 76 65 60 60. Okay. The area is 38.3. So 38.3 is, I think it's W. Yeah, it's W into 130. W18 into 130. W18 into 130. So it's I should change there. So I'll be changing that. It's W18 into 130. 38.2 and 3 4 5 6 7 8 8 9 10 11 12. Okay. 1 2 3 4 5. So it's W18 into 130. So our minimum would be 1 2 3 4 5. Yeah, 2.7. This is our minimum. I've selected this minimum of these two. So guys, you should know that this is W118 into 130. So this is a mistake. So I'll correct it in the slide probably. And so it's just a little mistake. Oh, okay. I'm solving it on AST. Uh, okay, finally, I have the slenderness ratio. It's simple. R minimum is 2.70. Same table would, I mean, same graph would be followed lambda r, and lambda r comes out to be 113. My slenderness ratio is greater than lambda r. My slenderness ratio comes out to be 116, and it's the same case. I mean, in the previous section, I have done it. We have done it for LNFT. So our major concern is geometric failure, because I am falling somewhere here. F critical would be computed as this, and it's very easy. And finally, I've been able to calculate the F critical equal to 18.8 KSI. The nominal load would be F critical into AG, and obviously this is 720 kip, so you have to divide it by a factor of safety, which is 1.67, because phi is 0.9 and factor of safety should be 1.67, so that the product of 2 gives us 1.5. So it's very easy lecture, and I mean, it's very easy to design. The basic concept is the basic thing is that the only point which is very valuable or noticeable is this: you don't know what Fy would be, although it's given that is 50 KSI. But if your column fails in material experiences material failure, then this would not be equal to 50 KSI. So that's why you can start with initial value of Fy, that would be F critical, and it may be 50% of Fy, but that design would be uneconomical, although you will get the right values. The best thing is to assume it to be 66.56% of Fy, or 70% of Fy is even good. It means your your column fails somewhere here, not at 50 KSI. It fails at the value of 35 KSI. So this is the only point which is very noticeable and very important. So I just want to change the value of this, and I'll keep it. I mean, I have to change this value. mm, this this is W18 into 130. So this is 130 here, and this is 130 here. Okay, thank you very much. I'll keep that.